Morning. Good morning.
Yes. Yes, yes. Yeah, I think that's not a motivation.
Yeah.
That's the only minor thing. That's a sample.
Thank you.
Morning. Hi, guys.
Just a little, just a little. Not a big.
Thanks, Young Chai. Sorry, emails. I saw it. I'll go over it.
No, it's not. That's. I don't like this. You like?
Yeah.
I don't.
Have many questions.
Yeah. Come on. Touch.
So it would be,
But.
is that clear?
Yeah. Yeah, that's common to what you were pointing out. So I'll go over it.
Never seen.
You're more than welcome to chime in too and add your own comments.
Yeah. I it's a new generation of dog. Yeah,
I would like to.
but you are much more stronger. More stronger. You are more.
Morning. Hey, good morning, everyone. We'll wait another minute or so here and then we'll go ahead and get started. Okay, good morning, everyone. I think we're going to go ahead and get started. So agenda for today, we're going to be continuing our discussion of variance estimation that we started on Monday. And we're first going to start off by going over homework number 1. So everybody has now had homework number 1 returned. So Young Chow and I just had a couple comments that we wanted to share about the job that people did in homework number 1. In general, everybody did a really nice job. Okay, so that was good to see. It's good to see people are thinking about the data sets that they want to work with. Just a couple points that we want to make, which came up repeatedly on homework number 1. First of all, in the question that was asking about the effective sample size, remember that the effective sample size is a product of your actual sample size and the design effect, right, for a given estimate. So who can tell me how the design effect is defined in terms of variances? How is the design effect defined?
Variance, it's a ratio proportional to the variance of the sample random sample.
Right, so it's the variance under the complex sample design of that estimate divided by the variance of the same sample size under simple random sampling, right? So the key point about this question is, what information were you given? You were given what in that third homework problem, homework number 1?
Complex sample size and design effect.
But were you given the design effect?
The ratio of standard error.
You were given the ratio of standard errors, right? Remember, the design effect is defined as the ratio of variances of a given estimate. Remember, the standard error is the square root of the variance, okay, to get the standard deviation of the sampling distribution. So what people miss there is you have to actually square that ratio of standard errors to get the actual design effects. Ratio of standard errors, sometimes that's called a DEFT. It's like a variation on the design effect. It's something you can use for those kinds of calculations. The point there was just to remember that the standard error is the square root of the variance. Okay, so if you're given a ratio of standard errors and you wish to compute effective sample sizes, you would need to square that ratio first before you do those calculations. Okay, that was the whole point of that question. Okay. Another terminology issue that came up had to do with just understanding of what we mean by primary sampling. Okay, so something else we want to revisit, remember the distinction between strata and primary sampling units. Okay, strata are fixed by design. They're all possible divisions of the population. Your sample is allocated to those different divisions defined by the strata. The PSUs are the units that are randomly sampled at the first stage of sampling within each of those strata. There was some evidence of confusion there in the homework about the terminology involving PSUs. and what exactly the PSU represents in a given sample design, remember that PSUs are randomly sampled. Strata are not. Okay, so when you're defining those features of the sample design that gave rise to the data sets that you're working with, remember to keep that distinction clear. PSUs are usually naturally occurring groups of elements in the populations, like neighborhoods or geographic areas or establishments or something like that. Okay, that's what we're actually randomly sampling. We're not randomly sampling strata. Strata are fixed by design. Remember, a stratified sample allocation, we're removing the between stratum variability from the sample entirely with that kind of design. Okay, we're definitely needing to account for between cluster variability within strata because that's what's actually being randomly sampled. Okay, everybody clear on that point? Other than that, there were just a couple minor issues. Couple issues related to what data set should be used on the actual assignments. Young Chow may have had some questions, but I saw very few email questions. Okay, so if you're stuck or you're confused about any aspect of the homework assignments, just write me an email or send a message through Canvas. Don't hesitate. Okay, don't hesitate. These 8 weeks are for you guys. Take advantage of our time. Okay, have conversations, set up meetings, send emails. That's what we're here for. We don't want you to get stuck and struggle in silence. Okay, so if you're not sure what data set to use or how a particular software procedure works or whatever the case may be, take advantage of our time. Okay, that's what we're here for. Okay. Okay, other than that, we are pretty happy. It looks like people are honing in on what they want to do for their final projects. That's great. Young Chow, did you want to add anything to any of those comments?
That's,
Okay, great. Yeah, just a couple minor errors here and there. Okay, bless you. All right. So again, today we're continuing our discussion of variance estimation. Before we jump into our discussion of replication methods as an alternative to linearization, are there any questions from our discussion on Monday about Taylor series linearization as the first variance estimation technique that we've been discussing? Bless you. Any questions from Monday's discussion about linearization? Everybody comfortable with the ideas? Okay, so key point about linearization that's going to become clear in a second here. To implement linearization, remember, we need those stratum and cluster codes. Okay, if we don't see the stratum and cluster codes in a given public use data set or a data set that you're working with, we need to think about alternatives. Replication is one possible alternative, but that assumes that a data producer has given you the replicate weights that you need to carry out these methods. We're going to talk about what that means. Okay? If you don't see stratum and cluster codes, which kind of takes linearization off the table, okay, and you don't see replicate weights, which is what we're talking about today, what can you do? What can we do if we wish to adjust our variance estimates to reflect complex sampling features? What's another alternative? If we don't have the information that we would need to input to the software to estimate variance, what's another alternative that we could use to adjust our variances? Just as a hint, I started off today's discussion with this topic.
Previous procedures.
We could use previous surveys, sure, but what would we draw from those previous studies to adjust our variances? To account for complex sampling features. Design effects, right? Thank you, Gary. So design effects. Remember, the design effect is a ratio of the variance under complex sampling divided by the variance under simple random samples of the same size. So if we don't have any information to compute a design adjusted variance, and we're essentially pretending that we had a simple random sample, what can we multiply that simple random sample variance by to get an estimate of what the variance should have been under the complex sample design? The design effect, right? It's an instant adjustment factor that lets us inflate most of the time the estimated simple random sampling variance to give us what we would have expected to see under the complex design. Now, the problem there is, remember, the design effect is specific to an estimate. So we'd want to try to get our hands on the design effect for that particular estimate that we're computing, and it may not be available. Sometimes, like Carrie was hinting at, we might need to look at an average design effect from a prior survey or a median design effect or something like that. And then multiply our simple random sample variances by that design effect. Now, here's a really tricky question. And this gave rise to a whole paper about 10 years ago. Okay? Suppose the data producer gives you weights, which allows you to compute unbiased estimates, may have an impact on the variances, like we've discussed, okay, but not the stratum and cluster codes, and not the replicate weights. Suppose you only have the weights available, right? What are we missing in terms of the variance estimates? So the variance estimates, if we say use linearization, that would account for the variability in the weights. What else are we missing?
Cluster addition.
Right, accounting for the intercluster correlation, and what else? What other feature of the design in general? Remember, there's kind of the big three for design effects. There's weighting, there's cluster sampling, and stratification, right? So we're not getting that gain from the stratification if the data producer doesn't provide us with that information. But remember, the design effects that you might get from a prior survey or documentation or whatever the case may be, they're going to reflect all three of those things: weighting, stratification, and cluster sampling. So if you're already using the weights for your estimation and your variance estimation, the variance estimates already reflect the variability due. So if you take those design effects from a previous survey and you multiply your variance estimates by those design effects, you're effectively double counting for the variability due to the weights, because those are already rolled up into the previous survey estimates, and you're accounting for the variability in the weights in your current estimates. So you're making your standard errors bigger than they need to be with that approach. So we wrote a whole paper on that topic about how to factor out that variability due to the weighting if you're forced to use this kind of design effect adjustment approach. It's like a double variance inflation, right? And that's a paper that's up on Canvas by West and McCabe, me and my colleague Sean McCabe. You can take a look at that if you'd like, but occasionally that problem will arise where you're looking at a data set that only gives you the weights, but none of the other design information. And you have to think about what's the best way to compute variances in that setting. Okay, something to think about. So take a look at that if you ever run into that situation. The good, the friendly data producers are going to give you what you need to correctly estimate the variance. Okay, they're not going to make your life difficult. So today, we're going to talk about an alternative to linearization that involves replication methods. And we'll talk about what this means. Okay, so just to review again our discussion of variance estimation thus far. We talked last week about the notion of a sampling error calculation model. And that's an approximation of the sample design that gives rise to the codes that you see in the data set, the stratum codes, the cluster codes, enabling variance estimation. We talked about the idea of ultimate clusters and how sampling error computation units get formed based on those ultimate clusters by collapsing, by combining, by random groups, all that stuff that goes on behind the scenes before you actually see the data set. Okay, so we talked about how those variables are formed. And then we've talked about linearization as a type of variance estimation thus far. This lecture, we're going to be focusing on replication methods as an alternative to Taylor series linearization and talking about the pros and the cons of using replication as an alternative technique. Okay, so as we talked about on Monday, the linearization technique is quite useful, okay, and we talked about it being the default in most of the software, if the estimate can be easily expressed as a function of sample totals. We can rewrite our estimate as a function of sample totals. Remember the weighted mean? That was rewritten as a ratio of two sample totals. Okay? We rewrite our estimate as a function of sample totals. Then we apply the Taylor series expansion idea to rewrite that complicated function as a linear combination of sample totals. Once we have that linear combination, we can write down the variance of that linear combination. And that boils down to taking the variances and covariances of sample totals. And we have known formulas that we can use to do that. That's the whole linearization idea. But the whole notion of Taylor series linearization requires those analytic manipulations and calculation of derivatives. So remember, we needed a smooth function of the data to begin with. That estimate needed to be a smooth function of the observed data, allowing us to take derivatives in the first place. Linearization is not directly suitable for non-smooth functions of the observed data, such as percentiles. That's a very common example where linearization has difficulty, because with a percentile, you may have many data points for a given variable that give you the same value of that estimate. Okay? 10 different people all have the 75th percentile on some variable of interest. So a percentile looks like a step function of the observed data. It's not a smooth function where we can easily take derivatives. So that's just a simple example of a descriptive quantity where linearization doesn't directly translate. The nice thing about replication techniques is that they're useful for almost any kind of estimate. Replication techniques rely much more on an algorithm than any kind of analytic manipulation, or any kind of calculus or anything like that. And that's what we'll be talking about today, but they have wide general applicability for variance estimation problems. Over the years, there have been a number of empirical studies comparing linearization with these other replication methods to see how well they perform. The vast majority of the conclusions are that the performance is nearly identical for the vast majority of different estimates. Okay? We'll talk about the implications of that. But in theory, people have shown mathematically that one procedure based entirely on calculus and analytic manipulations to derive variance estimates, that procedure converges to what the other procedure, the algorithmic procedure that we'll be talking about today, they converge to the same theoretical variance with a large enough sample size. So it's pretty wild that an entirely mathematical procedure and an entirely algorithmic procedure for deriving variance estimates both converge in theory with a large enough sample to the same theoretical variance. What that means is that for most cases, they both give you perfectly fine, valid variance estimates for what you're working with. So you might say then, well, what's the point? Like, how do we choose between these two if we're thinking about alternatives? Well, remember, linearization is the default, but the data producer has to give you the stratum and cluster codes, right? And in today's day and age, data producers are often very worried about disclosure risk. So the worry is that if I, the data producer, give you codes that have a stratum identifier and a cluster identifier, it's going to make it easier for a data snooper to try to identify a survey respondent. Okay? That's the thinking. My issue with that thinking is that I have yet to see a good study that actually demonstrates this kind of disclosure risk, these big national surveys and the data sets that are released. But that's the thinking. That's the concern. In theory, is that it's just additional information that somebody could use to help identify a survey respondent when we're supposed to be maintaining confidentiality for all of our survey respondents. Okay, so replication techniques give data producers an alternative where they don't have to provide the stratum and cluster codes, and instead they can just provide these replicate weights. And we'll talk about where the replicate weights come from. But all the data producer has to do is provide a bunch of additional weights. And that eliminates the need to provide the stratum and cluster codes. Okay, so that sounds nice in theory, but again, in practice, what replication requires is the data user to recompute their estimates of interest for every single replicate weight. So with today's computing power, we don't need to worry about that for means and proportions, all that kind of simple descriptive stuff. It's done in milliseconds, even if you had 100 replicate weights. Okay, to be used for variance estimation. The issue is with computation of more complicated models. Suppose you're fitting a structural equation model, or you're fitting some kind of complex multi-level model, where to fit one of the models, it takes a half an hour for the procedure to converge to some estimates. Now, the data producer has given you 100 replicate weights for the sake of variance estimation. To fit one model, are you going to wait 30 minutes times 100 just to get standard errors for that one model? That's the trade-off. And that's why linearization is the default computationally. It's quick. Quick computation makes the life of the data user easy. With replicate weights, you have to redo the analysis for every single replicate weight that's provided. And if that analysis takes time, okay, that could cause problems for those people who are working with the data. So that's the trade-off that we're going to learn about today. But these are the things to keep in mind in terms of what data producers are actually giving to the data users. These are the trade-offs to consider. Okay, but the empirical comparisons show that the choice of variance estimation technique really doesn't make a difference in most estimates. And we'll see additional evidence of that shortly. Okay, so how do these replicated methods work as an alternative? The idea of the replication methods is to use the cases that are already in your hands, in the sample data set that you have in front of you. Use those sampled cases to create replicates of the original sample. Okay? And the different replication methods vary in the way that those replicates get created. Okay? But we're using the observed data set to basically replicate or simulate or mimic the repeated sampling process, okay, to generate estimates repeatedly. So in the jackknife repeated replication idea, what we do is we leave out one PSU from the data set that you have in hand. Okay? You literally delete all the cases from that one PSU, and in the stratum where that one PSU is deleted, you adjust the weights of the other cases from that stratum to account for the PSU that was deleted. Okay? That forms a single replicate sample. Then we do it again. We delete the other PSU in that stratum. Then we delete the third PSU in that stratum, if it's relevant. Each time through, upweighting the remaining cases in the stratum where a PSU is deleted. And we repeat that for every single PSU in the sample. We're just taking out one PSU each time, reweighting the cases, and then creating that replicate. Okay? Now, each of those replicate samples under the jackknife is going to give you a unique estimate, right? Because we're deleting one of the PSUs. We're basically checking the sensitivity of your estimate to tweaking something about the sample. We're mimicking the idea of a sampling distribution with all these replicates, but we're doing it using the data set that we have in hand. Okay, so that's the basic idea of the jackknife. We'll dig into that a little bit more in a second. Another alternative is balanced repeated replication or half sample replication, BRR. This technique requires a sampling error calculation model where you have two PSUs per stratum. Okay? To use BRR in that sampling error calculation model, you need to have two PSUs per stratum. So those of you who have already looked at the NHANES data set for the class, we're going to see that a lot more on Friday, okay? Automatically ruled out. The NHANES sampling error calculation model, the first handful of strata have 3 clusters. Okay? To carry out BRR, we need 2 clusters per stratum. And that's why often data producers will create sampling error calculation models with 2 ultimate clusters or pseudo clusters per stratum. It allows data users to employ balanced repeated replication if that's been shown to have better properties for certain types of estimates. If the data producer provides anything else, the data user either has to create their own sampling error calculation model by doing their own collapsing and combine, which is a dirty business. We don't want to get into that. Or they're stuck with linearization or the jackknife as a more general approach. So BRR requires that sampling error calculation model with 2 clusters per stratum. Given those 2 clusters per stratum, we leave out one PSU, not just from a single stratum, like in the jackknife, but from every stratum. We literally delete half the sample to form the replicate. And then we upweight the remaining cases by a factor of 2 to account for the half sample that was removed from the observed data set. Okay, and then we do that again to form a second replicate. Then we do it again to form a third replicate, each time leaving out half the sample. Now, in balanced repeated replication, that's the whole idea. We don't do this in a haphazard fashion. We do this in a very systematic fashion so that we eliminate all the covariances between those half samples. That's the idea of balanced repeated replication. And we'll dig into that a little bit more shortly as well. Okay. And then there's the bootstrap. We'll talk about the bootstrap as well. That's where you take a width replacement sample of your PSUs of the same overall sample size as your observed data, and you form replicate weights for that with replacement sample. We'll talk about how those weights get formed. And then you do that over and over and over and over, forming many with replacement samples of PSUs, each time forming a new set of weights to form the different replicates. Okay, so 3 different styles of forming a replicate sample. For each replicate sample, you then create a revised weight. This is where the notion of the replicate weights comes from. Okay? So every time you form a replicate sample, you create a new weight, which adjusts for whatever deletion or whatever removal you did to create that replicate. And in addition, you may also reapply those non-response and post-stratification adjustments. Okay, we're going to come back to that point as well. Technically, each replicate sample should be calibrated to the exact same population, right? So all the replicate samples will always be referring to the same population. Okay, we should reapply those adjustments to each of those replicate samples. But that gives us a new adjusted replicate weight for all the cases in the data set for each of the replicate samples created. Okay? So this is what gives rise to data sets that some of you may have seen, where yes, you see that final survey weight for the entire sample, but then you see 100 other weights or 500 other weights. You're like, what? Which weight am I supposed to choose? There's 100 different weights here, right? They're all designed for replicate variance estimation. And we're going to talk about how those get specified to the software to enable replicate variance estimation. Okay? So now we have all these revised adjusted weights for each of the replicate samples formed. We then compute a weighted estimate of whatever our population quantity of interest is. Again, could be a mean, could be a proportion, could be an odds ratio. Whatever our estimate is, we recompute it for every single replicate sample using those new adjusted replicate weights. And that gives us several different replicate point estimates. If we were to plot all those replicate point estimates, guess what we would see? An estimate of the sampling distribution. We're literally mimicking the idea of repeated sampling with this idea. And we're just using different ways of forming the replicate samples. So then, given those multiple replicate estimates of our quantity of interest, we calculate a variance using those replicate estimates. Okay, so in one form or another, we literally calculate the variance of those replicate estimates, and then we take the square root to get our standard error. And we're done. Okay? There's no math here. There's no calculus. Whatever our estimate is, we can recompute it for each of the replicate samples. And that's all that we need for the actual variance estimation. All that we need are these replicate point estimates. So it's very attractive, again, from a data user perspective, from a data producer perspective, because they don't have to release those stratum and cluster codes. It can just create issues with computation, depending on the kind of analysis that you want to do. Okay? Given those standard errors, then, we construct confidence intervals, test hypotheses, same degrees of freedom calculations, okay? Because all the replicate estimates are based on the complex sampling features. What were the strata? What were the clusters? Those are all explicitly recognized in the formation of the replicates. Okay? So that's all taken into account. We have the same essential information to estimate variances, right? So those are the basic steps here. Now, by default, all the programs that we're going to talk about, Jackknife, Balance Repeater Replication, Bootstrap software, they adjust the values of the sample selection weights based on the way that the samples are formed. Like we said, for Balance Repeater Replication, the weights in a given replicate sample are simply multiplied by 2 because you took out half the sample. So you're upweighting the remainder to account for the half sample that was deleted. In the Jackknife, you're just adjusting the weights in the one stratum where the one PSU was taken out to form the replicate sample. Okay? That's the default in the way that the new replicate weights are formed. Theory suggests, though, that every single replicate weight formed again should reflect the same population and have the same adjustments applied. Non-response, post-stratification, or some form of calibration, those adjustments should be applied to each of those replicate weights, in addition to whatever adjustment was applied given the way that the replicate was formed. Okay? And we're going to talk about the software that can do that. Okay? Now, as a data user, right, you're not going to see the non-respondents. So you wouldn't be able to reapply the non-response adjustment. All you see are the respondents. So your only option as a data user would be to use some kind of calibration for each of those replicate weights. But again, the data producer ideally is not going to put that in your hands. They're going to do that adjustment for you before they release the replicate weights for public use. Okay, but there is software that lets the data user do this when forming replicate weights. It's kind of a proceed at your own risk thing. Okay. So in the end, with these replicate weights added to your data set, you see as many additional weights as there were replicate samples formed. So if the replicate variance estimation procedure produces 200 replicates, you're going to see 200 replicate weights. Okay, if it produces 50 replicates, you're going to see 50 replicate weights. Okay, it entirely depends on what type of replication procedure was used. And this is again where it's so absolutely critical to read the documentation for a given sample data set. Okay, what type of variance estimation procedure was used? Was it the jackknife? Was it balanced repeated replication? Was it bootstrapping? What variables in the data set reflect those replicate samples? What are my replicate weight variables? You never want to just guess as to what weight should be used where and what replicate weight should be plugged into the software. You've got to carefully read the documentation to understand what variance estimation strategy was used. And everybody here in the Summer Institute is more than happy to correspond with you if you're having a hard time making sense of the documentation for a given data set. You know, what should the replicate weights be? What should the final weight be? I can't find stratum and cluster codes. We're more than happy to help make sense of that. Okay? But most of you are also data producers. So these are things to think about when deciding what information about the sample design you're going to be giving to the public. Okay? Okay, so that being said, seeing replicate weights in the data set should never be scary at this point. They have a very specific reason to be included, variance estimation. They should never be intimidating. Okay, so here's a simple data example that we're going to use to illustrate some of these replication ideas. This is a data set, again, where you have 4 strata. You have 2 ultimate clusters per stratum, possibly based on a sampling error calculation model. You have 2 respondents within each of the ultimate clusters, just to keep things simple. The Y variable of interest looks like some kind of proportion. And then you have a final survey weight for each of those different respondents. Okay, so we have a total of 16 respondents. We have 4 strata and we have 8 clusters. How many degrees of freedom do we have for variance estimation based on this data set?
Number of clusters.
Yep, so how many is that, Isra?
Two clusters we have.
We have 2 clusters per stratum, right? So how many degrees of freedom do we have overall?
7.
Isra just said we need to take the number of clusters minus the number of strata.
4.
Right? So we have 4, right? We have 8 clusters in total, and we have 4 strata. So that affords us 4 degrees of freedom for the variance estimation. Okay. Okay, so that's our example data set that we're going to use to illustrate these ideas. All right, so here's what we're doing with the jackknife. There's several different ways to actually create jackknife replicates. The most common is the delete one method that I introduced, where you take one PSU out of the observed sample and you upweight the other cases. That is the default in most software that's going to allow you to create replicate weights on your own. Okay, is this delete one method. So for that delete one jackknife variance estimate, each of the strata contributes A sub H replicates. The number of clusters that were sampled from that stratum, that's how many replicates that particular stratum will contribute to the overall set of replicate samples. Okay, and for each replicate, one of the clusters in a given stratum is deleted to form that replicate weight. Okay, so in our data example that we just looked at, we have a total of capital H equals 4 strata, and we have 2 sampled clusters within each of the 4 strata. So the total number of required jackknife replicates for this default delete one jackknife method is 8. Okay, we need to form 8 replicates in total. But remember, we only have 4 degrees of freedom for variance estimation. So technically, 4 of those replicates are overkill, right? But that's how the jackknife works. This default procedure. Okay, so a jackknife replicate is constructed by deleting one PSU from one stratum. The very first replicate would leave out the first PSU in stratum 1. Okay, we literally just go down the list, leaving out one PSU each time. When we leave out that one PSU to form a single replicate, the replicate weight for that initial first replicate multiplies the weights for the remaining cases in that deletion stratum by a factor of the number of clusters sampled from that stratum divided by the number of clusters sampled from that stratum minus 1. So a simple idea with 2 clusters per stratum, if we delete one of those 2 clusters, we just upweight the remaining cases in that stratum by a factor of 2. 2 divided by 2 minus 1, okay? And so forth more generally. So the replicate 1 weight values would remain unchanged for the cases in all the other strata. So when you think about it, looking at that replicate weight, you could pretty easily determine who belonged to the first stratum in the first cluster. Because everybody else, if you compare their weights to the final survey weight, the vast majority of the observations are going to have the identical weight. Okay? What does change the replicate weight values is that additional adjustment. Okay? We apply an additional calibration adjustment. Maybe the data user also, or the data producer also provides an additional non-response adjustment. That's going to result in unique values of the weights for each of the different cases across the different replicates. But if those additional adjustments aren't applied, you're going to see a lot of overlap in those weights across these different jackknife replicates because we're only deleting one PSU to form a single replicate. Okay? Everybody with me on the idea so far? Okay, so here's how it would look in the structure of that data set. Okay, to form the first replicate, we literally delete the first cluster from the strata and those cases. Okay, and you see the weights of all the remaining cases. For the final 12 cases, their weights are unchanged. Okay, the only weights that are adjusted are the remaining cases in that stratum where the one PSU is deleted. And typically in the data set, you're not going to see a missing value for the weight for those cases that were deleted. You'll see a 0. Okay? That just tells the software those 2 cases that were deleted to form this jackknife replicate should not contribute to that estimate. Okay? So that's what gives rise to 0 weights on replicate weight variables that you see in the data set. Those are just cases that would not be included in a given replicate. Now, this is just the default adjustment. You can see multiplying those remaining cases by 2 in that first stratum. This does not include additional calibration or additional post-stratification. That's not shown here. But you could take the weights for these cases now and apply those post-stratification adjustments to make sure that you're mirroring what you know about the target population. And you would repeat this for each of the different replicates that you form. Okay, so here's just what the second replicate would look like. This would give rise to a second replicate weight. We delete the cases in the second PSU from the first stratum, upweight the remaining cases, possibly apply that post-stratification adjustment again. Now we've got 2 replicate weights. And so forth and so on until we've processed every single cluster in the data set. Okay, Terry?
So what would the deletions for the cluster?
I'm sorry, say again?
Are we deleting strata for the cluster?
No, the jackknife is deleting a cluster, right? So the jackknife, we're always leaving out one cluster. We're not deleting strata. Remember, we gotta keep those concepts clear. We still have 2 observations from stratum 1. Right? We're not deleting the entire stratum. We're deleting one of the clusters that was sampled or one of the sampling error computation units within that stratum. We're never deleting an entire stratum. Okay? Okay, so this is, oh yeah, George. Yeah.
I want to understand it's straighter. So they're numbered 1, 1, 2, 2.
Right.
But they're 8.
No, there's 4. Right? The first 4 observations are from the first stratum. There's missing values. This should be 1, 1, 1, 1, 2, 2, 2. This is just to show you the sampling of the clusters within each stratum. So in the full data set, you'd see 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4. Yeah, so jackknifing, we're taking out a PSU, not a stratum.
Because I was thinking like when you remove something, that's gonna make that why.
Yeah, no, that stratum code, just, visually think about filling that in all the way. We're just, the way we wrote this table is to show that in this first stratum, here's the first cluster. In that first stratum, here's the second cluster.
Oh, yeah, okay.
Yeah, Willie?
People applications. Check mine. Legal for surveys, taking samples.
Okay. It entirely depends on what a survey wants to do. They may choose to use the jackknife, they may choose to use the bootstrap. It entirely depends. There's no mathematical theory that says if you're doing a labor force survey, you should use the jackknife. It's entirely up to the data producer. Yeah. So we're just showing the first possible replication method. Yeah. Okay. Okay, so here for the data example, we're constructing 8 replicates, right? Because we have 8 clusters in that design. Okay. For each of those replicates, once we have that replicate weight, we compute the weighted estimate for that replicate. Okay. So in this particular case, our focus is on estimating the mean of that variable that looks like a proportion, that y variable. So for each of our different replicates, we compute the weighted estimate of that mean. Okay? So no different from the way you do your normal analysis for the full sample. We just reapply that analysis with the new replicate weight. So what that's going to produce are 8 different point estimates, 8 different unbiased weighted estimates of whatever our quantity is. Okay? This is all that we need for the variance estimation. That's the beautiful thing about these replication procedures. We don't need the stratum codes. We don't need the cluster codes. All that we need are these replicate weighted estimates from each of the different replicates that were formed. That's the essential information for our variance estimation. Okay. We also compute the full sample estimate the exact same way we would for any other procedures, okay, using our standard procedures that we've talked about. Okay. In this data example, that full sample point estimate weighted is 0.474 roughly. Okay. This is everything we need. That's it to make our inference. Okay. Now, there are variations of exactly what information can be used to form these jackknife replicates, right? So if the stratum and cluster codes are available in the data set, we can write down the jackknife variance in this way. Okay. We're explicitly recognizing the deviation of the one replicate around the full sample estimate, the sum of those squared deviations. We're also recognizing the number of clusters that were available within a given stratum. Okay. For the software to actually use this kind of formula, okay, it needs to be able to identify the strata and the clusters. Okay. If that information is not there, the software relies on this more general formation of the formula. But notice that if only replicate weights are provided, which is often the case in practice, the software is going to use this constant A-1 over A, okay, given the number of replicates that were created, total number of clusters. Okay. It's better in practice to fully reflect the replicate variance if you know what these specific coefficients are, as they're often called in the software, for each of the different strata. Because, for example, if one stratum has 4 clusters, right, this coefficient is going to be 3 divided by 4. If another stratum has just 2 clusters, this coefficient is going to be 1/2. Not everything's going to be equal to this constant value based on the number of replicates. So some data producers, in addition to giving you the replicate weights, will give you these coefficients for each of the different cases in the data set. So every case coming from the first stratum should have a coefficient of 3 out of 4. Every case coming from the second stratum should have a coefficient of 1 out of 2. You might see an entire vector of coefficients like that because the data producer wants you to use this particular variance estimation formula. Okay? So that's another piece of information that you'll see in the documentation that you should not be intimidated by. If the data producer says, here are the jackknife coefficients for all the observations in your data set, that's just referring to this piece here. If you're not given those coefficients, this is the variance estimation formula that you guys would use using each of the different replicate estimates. Gladstone, do you have a question? Okay, so again, if you have the full sample estimate and the individual replicate estimates, this is the only formula you need. Okay, so it makes the calculation pretty straightforward if only the replicate weights are available. And again, we're using the same degrees of freedom, given the information about the sample design. Okay, so in our current setting, okay, we would use 1/2. We know that that's a constant coefficient for each of the different strata here, and then look at the squared deviations of the individual replicate estimates around the full sample estimate. Okay, that calculation for the jackknife variance yields this quantity. Remember that we have to take the standard error. All right, we have to take the square root to get the standard error. Okay, so here's that operation. Then we can form a confidence interval. Full sample estimate plus or minus that critical t-value given 4 degrees of freedom times the jackknife standard error. And that's what the software is doing in the background. Now, this is the special case of 2 clusters per stratum. That's what allows us to use 1/2. But again, there could be different flavors of this variance formula depending on what coefficients you're provided. Okay? In this case, with 2 clusters per stratum, we know that coefficient is 1/2. It's the constant for everybody. Okay, so that gives us a 95% confidence interval as you see here. What we're going to do is build up this 95% confidence interval using each of the different variance estimation methods and see how they compare. Okay, so that would be our jackknife variance in this 2 cluster per stratum design. Okay, now thinking about the software that makes all this possible. For replicated variance estimation methods, data producers typically will give you a vector of replicate weights. For the jackknife, they may also give you a vector of coefficients. Okay? But generally, you're going to see a vector of replicate weights. And you have to, again, read the documentation carefully to understand, okay, what technique was used and how those weights should be input. This, again, eliminates the need to release the sample design stratum and cluster codes. Okay, so the data producer doesn't have to do that, and it enhances disclosure protection. But the data user still needs to know what replication method was used. Okay, so the data producer doesn't want to just give you 50 replicate weights and say go. Right? You have to know, was the jackknife used? Was BRR used? Was bootstrapping used? That's a required input to the different software because slightly different formulas exist for calculating the variance depending on the way the replicates were formed. Okay, so that's still essential information. And again, the data producer usually will also perform non-response adjustment and post-stratification for each of the different replicants to make sure that the individual replicate weights, again, mirror the population. All right. So if you're given that big, long set of replicate weights, usually tagged on to the end of a data set, the software makes it very easy to input them to the variance estimation procedures. Okay. So for example, in Stata, suppose we had a jackknife, we would say survey set, notice no cluster code comes after SBY set, right? Monday, we talked about when using linearization, that first variable that you specify after survey set is your PSU code, your cluster code. Notice it's missing, okay? Because it's not going to be in the data set for the replication methods, okay? Then you still need to specify your full sample final survey weight. That's our P weight variable in square brackets. After a comma, there's no stratum code. The stratum codes are missing. Okay? But we do have these replicate weights. Stata in particular makes it extremely easy to specify the replicate weights. Usually, replicate weights are going to be coded like WT1, WT2, WT3, WT4, all the way up to maybe WT100 or whatever the case may be. That's again the data producer being friendly and making it easy for you to specify those replicate weights to the software. If those 100 replicate weights all have different names and different numbers, that's very mean on the part of the data producer, because what you would have to do as a data user is literally type all 100 of those names as the set of replicate weights you want to use. Assuming that convention has been followed where you just have WT1, WT2, etc. In Stata, all you have to do is type the common alphanumeric piece of each variable name and then an asterisk. And Stata will pick up all 100 or all 98 or all 500 or however many replicate weights there are. It'll just pick up all of those different replicates to use for the variance estimation. So you don't have to type all that out, assuming the data producer has been nice to you.
You can rename them.
Or you can rename them,
To
but
avoid having a long code.
you can rename them, but that's no different from just typing those names in, right? Okay, we like to be lazy, right? So this makes it easy to be lazy, right? In addition, here we're using a jackknife, so we say JKR weight. That's the option that we're using here. In addition, VCE stands for the variance estimation method. The default in survey set is linearization, like we talked about. If we want to invoke a different kind of variance estimation, we just have to say what method was used to create the replicates. So in this case, we're saying VCE jackknife. Okay? This will then set these essential features of the complex sample design for all subsequent analysis commands. So we would run the subsequent analyses in the exact same way, okay, as we did with linearization. We're now just using replicated methods for variance estimation. And in Stata, as we'll see on Friday, you're going to see dots every time a replicate estimate is being computed. Okay, and that should be your hint that, okay, Stata is using some form of replicate variance estimation as opposed to linearization. And Stata will label your standard errors accordingly. It'll call them jackknife standard error, BRR standard error, bootstrap standard error, like we saw with linearized standard error, the example so far. Okay? So it's never a mystery exactly what method's being used. Okay? Little bit less straightforward in R, but still very easy to do. Remember, we talked about in R, you have to use SVY design to create a design object that you would then use in subsequent analysis functions. If you have replicate weights, you don't use SVY design. You use SVRep design to create your design object. Okay? And in SVRep design, first argument is your final full survey weight for the entire sample, then your data frame object, then type is the type of jackknife replicate variance estimation to use, JKN being the most general one that I just introduced, where you delete all the possible clusters. Okay? Then the R argument here, rep weights, is the same thing as JKR weight, okay, within Stata. In R, though, you have to pick out the specific columns in your data frame object that correspond to the replicate weights. So as I said in the comment here, this assumes that the jackknife replicate weights are contained in fields 50 through 100 of the data frame object. So it takes a little bit more work to identify exactly what those columns are that contain your replicate weights. This is where you typically, for an analysis, you're going to want to create your own data frame object where you know exactly what those columns are. Because suppose you made a mistake and column 50 was like somebody's blood pressure, right? That person's blood pressure would then be used to form that first replicate estimate. That's not what you want to do, right? So you have to be very careful in picking exactly which of those fields exist. And you could also use variable names as input there. There's different ways to do this, but this is just showing one possible way of specifying that vector. Then R also makes it possible to set up those coefficients via this R scales option. So here, we're just repping that coefficient 1/2. We know there's 2 clusters per stratum. We're just repping that 1/2 coefficient for all of the different cases in the overall sample, okay? So that 1/2, again, is that coefficient that I talked about in the jackknife. So you can specify those coefficients as another long vector if you want to, as a part of SVRep design. Stata also lets you do that. There's some other options that we'll look at on Friday. Okay? And then once you have that replicate design object, you can run whatever analysis function you want. You just input the name of the replicate design object this time, instead of the other design objects that we talked about previously. Okay? And proceed with your analysis. Okay, so pretty straightforward. We just have to identify where those replicate weights are and then input them to the software as in addition to the method of replicate variance estimation.
A question.
Yep.
For this data code in the previous slide,
Yep.
So suppose that we have friendly data producer and just say weight one, WT 1, 2, 3. So with this
Yep.
data code, with the asterisk, so this data will automatically compute 1, 2, 3
Right.
instead of, yeah, okay.
Yeah, that's what the asterisk is doing. It's just saying we're going to process every single replicate weight variable that starts with WT. Okay? So you do have to be careful. And again, this is where reading the documentation carefully is important. Okay, but that's a shortcut to doing this.
So do we have to, just to be on the safe side, do we have to double check the labels of the replicate weight to make sure they're all formatted that way?
Yeah, it's worth doing that again. The hope is that the data producer's been friendly and they didn't make a mistake somewhere along the lines in terms of labeling those different variables, but it never hurts to be very careful about this and just double check that, you know, there's not some random replicate weight that's coded like 98.9 or something like that, that doesn't fall into this integer order. It never hurts just to double check all those variables.
And we have to do that manually instead of having a code to help us check that.
Well, you can, like, for example, in Stata, you can use the same kind of shortcut to get a summary for every variable in that list. You can also use a hyphen to look at analyses for all variables in some list from point A to point B. In terms of the variable names, you can just use a simple hyphen. So there's different ways to look at results for those kinds of lists of variables. This is just one of them, so.
Thank you.
If you go to the, for example, columns 50 to 100.
Yep.
If I look through the columns.
That's your job to know. So you have to be familiar with your data set. You have to have read the documentation. If you're creating your own version of the data set, you have full control over what variables are in what position. So you have to know that. Right? That's part of being very careful about the management of a data set, is knowing exactly where those replicate weights are. Yep, Jared?
Can I ask what scale equals one is for? Is it for the JR?
Yeah, so that it has to do with the type of variance estimation formula used. So if you specify JKN, you have the option of specifying scale and R scales. Scale is another general factor that's multiplied by that coefficient. Usually for most of the JRR variance for estimation formulas, that's just going to be 1. What matters is R scales. That's where you would input the different coefficients. Yep. So that initial scale is usually just going to be 1. I saw, yeah, Jupiter.
So I just want you to come again. I think in the previous lecture, you and what you mentioned here is that the motivation for the data producers to provide the implication words is basically to maybe make the class type strata codes anonymous, or maybe to that they
Just remove them entirely.
yeah,
Not just make them anonymous, but get them out of the data set
Oh, yeah.
entirely.
So
Because people make the argument that even if those stratum and cluster codes have been masked or anonymized in some way, that somebody could still use them. I disagree, but people make that argument all the time.
So
Yeah.
they remove
Yep.
so they remove them entirely. So in the previous lecture, if I got you right, you did indicate at some point that if the final sample weights, if you get the coefficient of variation of somewhere above 0.02.
Yeah, for linearization, yep.
Yeah, then the linearization may not be appropriate to use. And then you indicated that we may have to use this.
Right.
So I'm just wondering whether the data producers are so careful that that could also be another motivation for them to provide verification weights.
Sure.
So do I, if I need to use a data set, for example, in case I check and I discover that that is not the case, that I don't see the replication weights.
Yeah, so great question. So you have stratum and cluster codes, you've used linearization, you find that coefficient of variation is like 0.3, but the data producer hasn't created replicate weights, right? There are procedures in the software that will create the replicate weights for you on the fly. right? So suppose I had my survey set in Stata and I had my cluster code, my P weight, my stratum code, so it's going to default to linearization. What you can do on the fly in a survey analysis command is say, for example, the same way that we did subpop, you can say SVY comma VCE jackknife. So that temporarily for that specific command changes the variance estimation technique to jackknife. For that one analysis, Stata will take all of the stratum and cluster codes and form the jackknife replicates for you, just in working memory. It's not going to save them in the data set. It'll just form those in working memory and go through and calculate the jackknife variance estimate. So you can do that on the fly, but what's missing there is there's no opportunity to do that calibration, right? It's just using that simple adjustment for each of those replicate weights on the fly without any calibration. So you can change it on the fly. And in R, you can use the function as dot SV rep design, and you can input your design object that was defaulting to linearization with the stratum and cluster codes, plug that into as.sv rep design, and that will spit out a replicate design object using a particular type. So like you could say as.sv rep design, input your design object, and then say type equals JKN. That will give you a design object with jackknife replicate weights. So as long as those stratum and cluster codes are there, you can also ask the software to create the replicates for you. In Stata, it's going to be temporary, specific to a given analysis. In R, you can actually create a new design object that contains those replicates, but neither of them are going to have that additional calibration adjustment applied. That's the key thing to remember. Yep, great question. Yep, Myra?
And this function as we have designed,
Yep.
will give to you a scale. Yeah. And the
Yes, so as part of as.sv rep design, you would need to input the same information like we're seeing here. So like if you're coming from stratum 1, cluster 1, you're going to have a coefficient of 3 out of 4 or something like that. At least you have the option of specifying that. Yep. But that's, again, you have to have this very intimate knowledge of the sample design. And that's where you really need to rely on the data producer to give you those coefficients for sure. Yep, George?
I want to find out if you are having a data set that is at data at provincial level, at region level.
Okay.
So in such a case now, this method which one does it treat as the straighter? Is it the region or the?
It's whatever you specify, right? So everything I just described, you're starting with a design where the stratum codes have been explicitly specified. In both cases I just laid out. So you've already explicitly specified those stratum codes. So whatever stratum variable you input initially, that's what it's going to use to form the replicates. So if you input the region or the province, it'll use that to actually form the replicates. So that's entirely on you. If you're using this on the fly method that Jupiter was talking about, it entirely is on you to make sure that you specified the right stratum code variable and the right cluster code variable. You never want to make that up, like we talked about. Those stratum and cluster codes should always be exactly what the data producer gave you. Never want to say, for this analysis, I'm going to use region for the stratum. For this analysis, I'm going to use province. For this analysis, I'm going to use never want to do that. Because you're just completely breaking the whole idea of the sampling error calculation model.
I've got
Great
question.
Yep, Sarah.
Okay, so I've got a data set I'm looking at that they provide the jackknife 30 variance weights, the actual base weight, they've stripped any straight, etc. Is there a way to do the analysis you've been talking about prior, where you look at the distribution of certain subpopulations within? Well, I can't because straight and cut. So I'm struggling with that because I'd really like to, but I don't see any way how to.
Yeah. If you don't have the stratum and cluster codes, you can't look at the distribution of your sample across those codes or for a subpopulation, but it's irrelevant. That's the point. For linearization, all that stuff that we talked about and we'll continue to talk about variance estimation using the unconditional approach that we discussed, that's only relevant for linearization. It completely goes out the door with replication techniques, because with replication techniques, all that we need for the variance estimation are the replicate estimates. It doesn't matter what subclass those were formed for, it just doesn't matter. All we need are the replicate point estimates. We don't need the
Okay,
stratum and
understood.
cluster codes, we just need the replicate estimates. So that notion of unconditional versus conditional subpopulation analysis that we were talking about, irrelevant.
Yes,
Replication methods.
okay.
Yep.
Okay, so across the board, it's not just for variances. Okay,
Just for
thank
that
you.
issue, just comes up with linearization where you're dealing with explicit stratum and cluster codes. Yep.
Okay, thank you.
Okay, I think this is a good time for a break. So we're gonna take a break and then come back and talk about balanced repeated replication and bootstrapping and how to carry those out. And then we'll do some empirical comparisons. And that'll take us through the end of today's lecture. Okay, so let's take about a 5-minute break and I'll start up at about 11 after with the remaining replication methods. Okay? Okay, thanks everyone. Yeah.
Geez. Jesus.
No. That's not a relevant file.
Yeah, but I thought it was the file of chapter.
No.
homework one.
It was telling you to use the ESS data. We talked about that in class as well. For that first homework assignment, you had to use ESS.
Yeah. Okay.
Yeah.
Could it be considered if I did the homework right, in the right way? Because you were very interesting. I didn't send you the homework again because I thought that the time was out and I could send you doing the homework with this.
Yeah, just if you want to redo it, that's fine.
Can I send it?
Yep, just do that.
How can I?
Just email.
Okay.
But yeah, again, like send an email if it's not clear. If you're looking at this data set or some other file, and you say, I'm not sure.
I'm wrong.
Yeah.
But I'm wrong. Okay, but I thought that, and I thought that the name of the variable, because in this data set, the name of the variable is y, and I thought that the y was the
Just
okay,
ask.
okay, but
Just resend it by email and we'll take another look at it.
I didn't realize that my colleague said after the time during lunch, and I thought, oh,
That's okay.
I missed
It's
it.
okay. It's okay. Just resend it by email and we'll take a look at it.
I will send you our homework.
Yeah, that's fine.
Okay,
That's fine.
okay. Thank you very much.
Some of those. My problem was what
The which method? Suit? Swift. No, I have not.
That's the reason why I was thinking like teams I have for the living conditions and like sort of like put in there was a survey that was done. Then they used the model as a previous estimates. Sort of model the
Yeah, you can to model the variances, you mean, or to model like.
if the estimates were
I guess I'm not sure. So there's techniques where people model the variance estimates, and then you can predict what the variance estimate will be for a given estimate in use survey. But I'm not sure what you mean by modeling the estimates. Yeah, I don't know what that means. So, I mean, there are different ways you could develop modeling procedures to calculate estimates, but we could have it in a meeting maybe, or we can look at a meeting. We can't look at it right now, but yeah, if you want to set up a meeting to discuss it, that's fine. But I haven't heard of that Swift idea in general, and the idea of modeling either estimates or variance estimates, it's going above and beyond like what we're introducing in this class. So my preference would be that you carry out an exercise that demonstrates what we're talking about in this class, because those are certainly relevant procedures. But again, we want everybody in this class to demonstrate that you can handle these design-based approaches. And once you have these mastered, then those model-based approaches are like another step. So I think ideally, if you could demonstrate using a methodology that applies to one of the data sets in this class, that would be the best way. Yeah, I mean, again, like you could do it if you wanted to, but given this purpose of these 8 weeks, we really want you to be able to just demonstrate these design-based approaches. So, yeah, but if you want to meet and talk about it further, just shoot me an email. We can set up a time. I mean, see, that's the thing. I don't know, like, given the 8 weeks that we have, if this was a full semester course, maybe. But I don't know if it would be wise to dedicate a lot of time to trying to understand a complicated modeling method as opposed to just trying to find a data set where you can implement these techniques, right? I think it's more relevant for this class. Something to think about.
I understand.
Yep, yep.
Yeah. Data producer that gives the microdata with only the replication rates, and they give it the scale, the everything. Because in my company we give our microdata in this way. We use Bootstrap, but now I realize that we don't give the scale but sometimes we get the microdata with the R data, and the R is an object with the design.
Yeah.
So the design is read. You only have to use the survey package.
So the actual design object is provided with the data?
Yes.
Interesting.
But we give a CSV file too for users that don't know how to use R.
Right.
And this part, I think we are not doing well because we don't give the scale, for example, and the type of the bootstrap.
Remember that scale is just for the jackknife. It's not relevant for the bootstrap. We'll talk about that. We haven't talked about the bootstrap yet, but
I have a scale. I have a number of scales.
Well, we'll talk about one possible bootstrapping method that's used. It just, if you have a bootstrapping method where there are different scale coefficients for different strata, like that's understandable, but I'm going to introduce kind of a more general approach that makes that irrelevant. So, but if you do have it for a given variance formula and you're not providing it, then yeah, that's an issue.
Yeah. But you have an example that data producers in the United States, I don't know, that give the scale in a website.
Oh yeah, so like one of our papers, like I think it was called the Survey of Doctorate Recipients. They actually gave us SAS code that just laid out the entire vector of coefficients, and we had to read that into SAS and then do the analyses based on those scales. So yeah, so there are examples out there, and usually, yeah, it's going to be in documentation for a given service. But yeah, if the bootstrap formula that you're using has those coefficients, yeah, it has to be there. So, yep. Okay, why don't we start back up again? Here. Okay, so we've talked about the jackknife as a general approach. Now we're going to talk about balanced repeated replication as another type of replication approach, another approach to creating replicates. So balanced repeated replication is also sometimes referred to as half sample replication, as we said, because you're deleting literally one PSU from each of the different strata. You're taking out half the sample. And this does assume what's called a paired selection design, where you have 2 PSUs per stratum to carry this out. A half sample replicate is defined by choosing 1 PSU from each of the strata. And we don't do that at random in balanced repeated replication. That's the key point here. This is not done at random. It's done in a very systematic fashion to make sure that the different half sample replicates are balanced with each other. Okay? So when you form a half sample replicate, the complement of that half sample replicate is also a half sample replicate. So different bootstrap or different balanced repeated replication techniques, some take advantage of those other half samples, some don't. Okay, so there are a lot of different ways you could go with balanced repeated replication in terms of how you do the variance estimation, because you're always creating 2 half sample replicates every time you delete half the sample. Okay? So in total then, there are 2 raised to the capital H, where capital H is the number of strata. There are 2 raised to the capital H possible half samples and their complements. So a number of different possible half sample replicates to choose from, but we only need capital H half samples for variance estimation in the end. Why? Who can tell me? The abbreviation is DF. What does DF stand for? Degrees of freedom, right? With 2 clusters per stratum, we have capital H degrees of freedom. So sure, we could form 2 raised to the capital H power balanced replicates. We could give those to the data user. It's all overkill. We only need a capital H balanced replicates to estimate variance. Okay, so we do that in a systematic fashion. That's the whole point here. We don't do that at random. All right. So here's one possible choice of 4 half samples. Okay. You see for each of the 4 strata that we have in our toy example that we've been talking about, okay, the first half sample replicate is formed by taking the first PSU from stratum 1, the first PSU from stratum 2, and the first PSU from stratum 3, and then the second PSU from stratum 4. Okay. Second half sample replicate is formed by taking the first PSU from stratum 1, and then the second PSU from strata 2, 3, and 4. Okay. This is done in what's called a balanced fashion. This 4x4 matrix of pluses and minuses that you see here is what's called a Hadamard matrix. Okay. These Hadamard matrices have the nice properties that basically across the different half sample replicates, the pluses and the minuses cancel each other out, okay, in terms of the covariances of the estimates from the different half sample replicates. So balanced repeated replication relies on the formation of these Hadamard matrices. They have their origins in design of experiments, where you form a full factorial design looking at different experimental factors. That's where these matrices came from. They have this balancing property that the different replicates have no covariance in aggregate. Okay, we're eliminating the covariances between the replicates in the way that the half samples are being formed. So the nice thing about these Hadamard matrices, they've already been tabulated for factors of 4, 4x4, 8x8, so forth and so on, all the way up to very large numbers depending on how many strata you have. And we'll talk about how to deal with that, but all of them already exist in the software, much like we talked about with linearized variance estimation formulae. All these Hadamard matrices have already been tabulated. So you can use any one of these to create balanced repeated replicates that have that nice balancing factor, okay, where the covariances of the half samples cancel each other out. Okay, so you can take this idea of a Hadamard matrix all the way back to a 1946 paper by Plackett and Berman. And again, this was written in the design of experiments literature, but that's where the idea came from. And again, these have all been tabulated for all these possible multiples of 4, 4, 8, 12, etc. And the software that we're talking about in this class has algorithms available to create these matrices. So again, not something that you have to worry about. And again, these matrices simplify variance estimation by eliminating the covariances between the different replicates in aggregate. Okay. Now, given that these matrices are all a function of 4, what happens if the number of strata that you have In our case, we had 4, right, in the toy example. What happens if the number of strata that you have is not a multiple of 4? Okay, in those settings, we can only achieve partial balanced. So we would refer to that as partially balanced repeated replication. Okay, but if we have a number of strata that's a multiple of 4, we can achieve full balance in this case, eliminating these covariances. So what happens if you don't have a multiple of 4? You take the matrix with that's equal to or higher than the number of strata that you have. So for example, if you had 3 strata, you would use the 4x4 matrix and drop one of the columns, okay, to get you back to 3 strata. You don't have the full balancing property because you don't have that 4th stratum to define the balanced matrix. If you had 5 strata, you would pick the matrix with 8, the 8x8 matrix, and drop the 3 strata at the end. Okay? That's the next best that you can do in terms of these matrices and partial balancing. And that's what the software is going to do to form the replicates. Okay? The drawback with partial balancing, if you still have some covariances between those sample replicates, the variance is going to be a little bit larger than it should be under partial balancing because those covariances will tend to reduce the overall variance. Okay, so back to our toy example, suppose that there's capital H strata with A sub H clusters per stratum. So again, 4 and 2 per stratum in our example data set. We form a balanced repeated replicate given a Hadamard matrix. Okay, we always have to start with the Hadamard matrix. We don't do this off the top of our head. We start with a Hadamard matrix, and then we systematically follow what that Hadamard matrix tells us to keep in each of the different strata. Okay, so we would delete one PSU from each stratum according to the pattern in a given Hadamard matrix. So in our example here, that first replicate would leave out the second PSU in the first 3 strata and the first PSU in the 4th stratum, following that Hadamard matrix. And then for the cases that we keep in that half sample, we multiply their weights by a factor of 2 to account for the half of the sample that we just took out based on that first row of the Hadamard matrix. And then we repeat that for all the other half sample replicates that we need up to capital H. Okay? That's the way this works kind of algorithmically in the background. All right, so this is what the first BRR replicate would look like in terms of our data example, given that Hadamard matrix on the previous slide. We would keep the first cluster in strata 1, 2, and 3, and keep the second cluster in stratum 4, and upweight all those remaining cases by a factor of 2. So everybody gets their weight multiplied by 2 to account for the half sample that was just deleted. Okay, that's our first replicate weight according to BRR, right? And again, all those missing values would usually be set to 0 in the data set for that first half sample replicate. And we might calibrate those values for the remaining 8 cases in the data set. Okay, that forms our first BRR replicate. And then the second replicate would leave out the second PSU in stratum 1 and the first PSU in strata 2, 3, and 4. Again, not arbitrary, not done at random, all based on the Hadamard matrix that has the nice balancing property across the replicates. Okay. Okay, we again upweight the cases that remain by a factor of 2, and so forth and so on. Okay, we form the remaining 2 replicates to get to capital H. Okay, so this is just what the second one would look like, going back to our data example, multiplying all those remaining weights by a factor of 2. Okay, so now we have our 4 replicates. We go through, we compute our weighted estimate using the replicate weight for each of those 4 replicates. Okay, that's that Q sub R here. So unlike the jackknife where we had 8 estimates, here we just have 4, according to this procedure. Those are the 4 estimates that we would use for variance estimation, along with the full sample point estimate. Okay, that's all we need. Right, just a different way of forming the replicates. Now, different way of forming the replicates, slightly different variance estimation formula. There's actually a number of possible variance estimation formulas that we could use depending on how the half samples were formed. This is just one possible approach that we could use here. Okay, so what we're doing, looking at the sum of the squared deviations of the replicate estimates around the full sample estimate and dividing by the total number of replicates. Okay, very straightforward way to calculate the variance here. So using this formula, there's the variance. We take the square root to get our standard error, form the same confidence interval, same degrees of freedom as we did before, and calculate the 95% confidence interval. Now, line that up with the jackknife confidence interval. They're almost identical. Okay? And this is that first inkling where it really doesn't matter what variance estimation method is used, you're going to arrive at the same general inferences. What it boils down to is what the data producer wants to provide in terms of the replicate weights and the design information. Okay, it really doesn't make a difference in terms of the quantitative inference that we would be making in this case. Okay, so that's half sample repeated replication. We'll talk about cases and examples where empirical simulation studies have suggested that the half sample procedure actually works very well relative to these other variance estimation procedures for very specific kinds of quantities. So every now and then you might run into a quantity where a data producer says you should really be using BRR to calculate variances for this quantity. So it's important to be aware of how to do that using the software. Okay. A third type of replication method is the bootstrap. And the flavor of bootstrapping that I'm going to be talking about here is the Rao-Wu rescaling bootstrap, which is it's implemented in a lot of the different software. Okay, so in general, the variance estimate based on a capital B bootstrap estimates is based on this formula that you see here. So the general theory of bootstrapping is you take a width replacement sample of the same size as the sample that you've selected. Okay. So if you had a simple random sample of 100 cases, you would take a width replacement sample from the observed data of the same size, okay, 100 cases, calculate your estimate based on those 100 cases in your width replacement sample, save that point estimate, and then do the same thing again, and again, and again, and again, for hundreds, even thousands of bootstrap sample replicates. Then you would use a variance estimation formula that looks like this, where you take a given bootstrap estimate, subtract the full sample estimate, square the difference, sum those across the bootstrap replicates, and divide by the number of replicates. Very simple idea, very powerful idea in basically simulating a sampling distribution for a variety of different estimates. The complication that arises in complex samples is what to do about the design features, the strata, the clusters, the weights, etc. We can't just take a simple width replacement sample of all the individual respondents in the survey data set. The width replacement selection has to respect the clusters that were actually sampled. Okay? And so the specific way that a bootstrap sample is selected depends on width replacement sampling of the clusters, not the elements. In the case of complex samples, that's the complication here. Okay? But in general, the theory of bootstrapping says that with a large number of bootstrap replicates, if you were to plot a histogram of all the replicate estimates that come from those width replacement bootstrap samples, you'd start to get a picture of what the true sampling distribution looks like. So we can simulate what the sampling distribution would look like for any possible estimate. It's a very general purpose procedure in the larger field of statistics. Okay? So we can do a lot of different stuff with that simulated sampling distribution. But with complex samples, and this is what Rao and Wu were talking about in this particular series of papers, you would form the capital B bootstrap replicates by sampling with replacement M sub H PSUs from each of the different primary state strata. So you sample those PSUs with replacement from within each of the different strata. And Rust and Rao, in a follow-up paper, suggested using A sub H -1 as that value of M sub H for the general performance of the bootstrap in this context. So that just means set M sub H, how many PSUs are being sampled with replacement, equal to the actual number of clusters sampled in that stratum -1. And that's what you use for that M sub H value. Okay? In that setting, where
for the operations of the exit doors of this aircraft.
Sorry, Sarah, did you have a
It's
question?
also unlikely, but if necessary, oxygen
No.
masks will drop from the
No.
Okay, thank you. So in that setting where M sub H is equal to A sub H -1, the bootstrap weight that would be computed for that selected replicate is what you see here. You take the final survey weight, you multiply by the number of clusters divided by the number of clusters -1 from that individual stratum, if they're in your bootstrap sample, okay? And then you multiply by the number of times that PSU alpha was selected in that particular replicate, okay? So this is a complex combination of all these different features, but that's where the replicate weight for a given survey respondent in a given bootstrap replicate would come from. Okay. So basically, every single respondent in a given replicate is going to have a weight computed in this way. There are going to be no weights of 0, okay, for this particular type of approach. And that's the idea of this rescaling bootstrap that Rao and Wu formulated. So this is where the actual replicate weights come from, following this bootstrapping idea where you're sampling the PSUs with replacement from within a given stratum. Okay, so software has implemented that Rao-Wu rescaling bootstrap. Okay, so you can request that kind of bootstrap approach. There are different bootstrap variance estimation formulas that are used. This is not the only one, but this is a popular one in the setting of complex samples, where you have to deal with straight-end clusters in terms of how the bootstrap sample replicates are formed. And what this boils down to is, again, specifying those provided bootstrap replicate weights, specifying that the variance estimation type was bootstrap, and then the appropriate variance estimation will be carried out. Okay, so that's another alternative for this kind of variance estimation. We'll see examples of that on Friday. Okay.
Before you
Yep.
proceed,
Yep.
The previous slide.
Yep.
That would be the case of one stage.
Yeah, well, this is the general case that we talked about with sampling error calculation models, right? The sampling error calculation model gives you a first stage stratum code and a first stage PSU code. So this is all in that general framework of sampling error calculation models. This is how the bootstrap sample replicates will be formed based on sampling those PSUs. There's no recognition of second stage elements, just because most sampling error calculation models just refer to the first stage. Yep. So this general approach only refers to PSUs. Because again, that's what dominates our variance estimates. Other questions about bootstrapping? Okay. Okay, so this is just another empirical comparison. And there's a couple important points to look at here based on this table. So what we did in ASDA was we looked at this NCSR data set, and for 3 different quantities of interest: the probability of having major depression, the probability of being diagnosed with alcohol dependence, and then the mean household income. Okay? For each of these 3 different quantities, we calculated variance estimates reflecting the complex sampling features using linearization, the standard delete one jackknife, and then balanced repeated replication. And what this table shows, first of all, is that your weighted point estimate based on the full sample should not depend on the variance estimation method. Okay, that's the first key thing to recognize here. If the weighted point estimate that you're computing changes depending on the variance estimation method, something is wrong. Okay, you should always be computing the same point estimate, regardless of what variance estimation method you're using. You're just using a different method of estimating variance to describe the sampling variability in that particular estimate. Okay, so that's the first thing to know. Second thing to note, look at the standard errors following these different approaches. Linearization based entirely on calculus, okay? Jackknife, balanced repeated replication based on algorithms. It's almost like a magic trick, right? They're almost identical to the 3rd decimal place, okay? Based on this large complex sample. For most types of estimates, it just doesn't matter what variance estimation method is used. The key thing is that you use a variance estimation method that takes the sample design features into account. And you don't pretend that you're working with a simple random sample. That's the most important thing. That aside, it's up to the data producer what information they want to provide. Okay? They want to provide stratum and cluster codes for linearization, that's fine. If they want to just provide replicate weights, that's fine too. Data users are going to arrive at the same general inferences. Okay? So it really boils down to what the data producer wants to do. Okay? Here's another empirical comparison. So this particular data set is coming from the health and retirement study, one of the early waves of the HRS. What we did is we extended that previous table even further. Okay? So here are all the different variance estimation methods we compare. First of all, ignoring everything. Assuming you have a simple random sample, which sadly, like I said at the beginning of class, is what the majority of data users do. Okay, that's what we're training you guys to not do. but let's see what happens. Let's assume that we have a simple random sample, okay? Second, we looked at balanced repeated replication and jackknife repeated replication using software, in this case Westfair, that lets the data user incorporate calibration adjustments to each of those replicate weights, okay? So in other words, we want to see what happens if using BRR and JRR, but also incorporating those same calibration adjustments to every single replicate to make sure that the weights always sum to the same population distributions, okay? Westfair makes it easy to do that. You can also do that with an R pretty easily, okay? Third, we looked at SAS, and we took the default linearization, balanced repeated replication, and jackknife repeated replication approaches using only that full sample weight and the default creation of the replicates, using those default adjustments, multiplied by 2, or upweight the people in the deletion stratum without any additional calibration, okay? So no additional calibration, no additional non-response adjustment, just the default adjustments in the formation of each replicate weight, okay? So the interesting comparison that I wanted to see was between these two approaches. Does it make a difference if you also calibrate each replicate weight? And then finally, in R, we looked at that Rao-Wu rescaling bootstrap using the full sample weight, where again, we didn't redo those adjustments for each of the different replicates. We just took the Rao-Wu rescaled weights as I described on the previous slide and used the standard bootstrap variance estimation formula. Okay. So we're going to look at means, a descriptive quantity. We're also going to look at regression coefficients. So using these different approaches, we looked at descriptive estimates, and we also fit a regression model. We're going to compare what we see across these different sets of results. Okay, so this is the descriptive table. You see the unweighted sample sizes from the HRS. Okay, so that's unweighted sample sizes used to compute these estimates. Then you see the weighted point estimates. Okay, so the weighted mean for years of school, about 12.3, a little more than high school here in the US. The weighted mean of body weight, 172 in pounds. And the weighted number of words that they could recall out of 10 if they're given a list and then asked to recall words in that list, just a measure of cognitive functioning. So that's a weighted point estimate, was about 7.5. It's actually a fun test, if any of you have ever done that. If somebody just throws 10 random words at you, and then they say those 10 words again, you get all 10. It's an interesting measure of cognitive functioning. Okay, I don't. Okay, now the remaining columns, okay, those are the 7 different methods that we compared. Okay, starting with assuming a simple random sample, the Westfair versions with the additional adjustments, linearization, non-adjusted BRR and GRR, and then the Rao-Wu rescaling bootstrap. Okay, main points to take away from this table are this column versus everything else, right? Look at the standard errors based on all those different approaches, different levels of complexity, different ways that replicates are being formed, use of linearization given stratum and cluster codes. It doesn't matter. Okay? What matters is accounting for the design features in one way or another, not just assuming simple random sampling. That's where you see the biggest difference between these different approaches, where assuming a simple random sample severely understates the standard errors because you're not accounting for the design effects. And this is showing you that linearization and the replication techniques both give you perfectly fine ways of accommodating those design effects in the standard errors. Again, agreement to usually the 3rd decimal place. Okay, so this is for descriptive estimates. So the next question we wanted to ask was, okay, what happens if we're looking at a regression model? Okay, so this was a linear regression model where the dependent variable was the number of words that they could recall, that measure of cognitive performance. And the predictors were gender, whether you were Black, whether you were Hispanic, and then the number of years of schooling that you had. Okay, just an arbitrary regression model to see what happens here. So again, you see the weighted estimates of the regression coefficients in this particular model. And again, same story, okay? Compare the simple random sample column, where you're assuming that you have a simple random sample, to everything else, okay? Same basic story. Even for the case of regression, it doesn't really matter what technique you're using. to estimate the design adjusted variance. It just matters that you're using it. That's the main takeaway point. So it shouldn't matter if the data producer gives you stratum and cluster codes or they give you replicate weights. The key is that you use that information to make sure that your standard errors are reflecting these design features one way or another. Doesn't matter if it's descriptive estimation or regression modeling or whatever the case may be. We've got to make sure that we're accounting for these design features one way or another. The specific strategy, for the most part, doesn't really matter. Now, moving forward in the class, we're going to talk about specific cases of estimates where there's some evidence to suggest that a particular method may have better performance. This is going to come up for quantiles in particular when we get to quantiles next week. Okay? But for the most part, most of the common estimates that people are interested in working with, it just doesn't. And this matches theoretical properties. Again, these variance estimation procedures converge to the same theoretical variance with a large enough sample. Okay. Okay, so that's what I wanted to say about replicated variance estimation. On Friday in the lab, we're going to walk through different methods of variance estimation, focusing primarily on the NHANES data. And we'll see both in Stata and in R explicitly how to incorporate different kinds of sampling error calculation models, how to set up different kinds of variance estimation procedures. And we'll look at a variety of descriptive estimates and compare the standard errors, again, following these different approaches. But the plan for Friday is to walk through the code in detail. And so for this particular lab, I really want you guys to try to follow along and mimic some of the code that we're going to be executing on Friday so that you can start applying these procedures to your own data. Okay? Okay, questions? Is there any?
For this one on Friday, we are going to take half of the
Just descriptive. Yep. So the focus this week and next is going to be mostly on descriptive estimation. We're not going to get to regression until probably around the holiday, the week of July 4th.
Based on this one.
Yep.
If I'm going to make a paper, for example, and I would like to see the difference between the three.
Yep.
So this one here, it's almost the same error, but to present, what about TSL?
There is, it's the best one, but remember, it looks the best in terms of just comparing these actual point estimates. Remember that all of these are point estimates, right? We are estimating variance. So in theory, I could put a confidence interval on this variance estimate. And all of those confidence intervals would overlap with each other in this kind of table. That's why I'm saying it doesn't matter. If you just look at the numbers, the point estimates of the variance, yeah, it looks like TSL may give you some advantages, but in terms of forming confidence intervals, it's not going to matter. That's it. It's an important thing to remember. This is variance estimation. Okay? I could add a standard error to each of these estimated standard errors. Okay? There's uncertainty with each of these point estimates. Okay, other questions? Yep, sorry.
Slide 16.
Slide 16. Okay.
So, plus first element selected minus the second element
right
selected. So,
I'm sorry, what was your question?
I did not get this plus.
So plus that says if when you're selecting the first half sample, okay, so for the first half sample replicate you form, we're going to keep the first PSU from stratum 1, the first PSU from stratum 2, the first PSU from stratum 3, and then the second PSU from stratum 4. That's how we're forming the first half sample replicate. Okay, we'll calculate a weight for that half sample replicate and then set it aside. Now we form the second half sample replicate. To form that replicate, we take the first PSU from stratum 1, and then we take the second PSU from strata 2, 3, and 4. That gives us a second half sample replicate. We form the weight for that half sample, set it aside. Then we do that 2 more times for the remaining 2 half samples. Okay, so that Hadamard matrix is what we follow like it's gospel when we're forming these half sample replicates. We don't form the half sample replicates arbitrarily.
Then people are
I'm sorry, say again?
what's the BPR?
The BPR, what?
Yes, the BRR.
Oh, BRR, yes.
Yeah. So in the jackknife, we have this one in each stratum, deleted one.
Now, in each stratum, in one stratum,
One stratum.
we delete one PSU to form one jackknife replicate.
Yes. And in BRR, how many clip?
Half. That's why it's called half sample replication, right? Because remember, we have
So how?
remember, BRR requires 2 clusters per stratum, right? So if we're keeping only one cluster in each of the different strata, we're deleting half of the sample.
So it's four clusters in one stratum.
No, remember, go back to the very definition of half sample replication. We require 2 clusters per stratum. If you give me a data set that has 4 clusters in one stratum, I can't use BRR. We require 2 clusters per stratum. People have written papers about that. Like, well, can we use BRR if we have 3 clusters? Here's a way to, nothing compares to this original design. Okay? It requires a sampling error calculation model where you literally have 2 cluster codes in every stratum. It's a requirement. Yep, listen.
And can you come to the with plus and minus?
Yep. Mhm.
At the fourth stratum.
Yep.
You just select at the second, yes, the second element.
Yep, every time.
Yeah.
This is one possible 4x4 Hadamard matrix that has these balancing properties. You might have another Hadamard matrix where you select the first PSU from the 4th stratum every time.
Could it be minus, plus, minus, plus?
It depends, right? You have to go through and establish that balancing property, that all these pluses and minuses cancel out with each other across the half.
Okay, this is one of.
This is one possibility.
Okay.
Yep. There are many other 4x4 Hadamard matrices.
Okay.
This is just one possibility that has that property. Yep. The software essentially takes one at random from all the possible of size 4x4. Any other questions about the techniques that we've talked about today? Okay, yeah, so Friday in the lab, we're gonna get a chance to explicitly walk through the code, practice all this stuff, try these different approaches. And then at this point, with your final projects, you should be honing in on, again, what the sampling error calculation model is and starting to apply some simple descriptive analyses and thinking about the final project and what you like to do. And then next week, that prospectus is going to be due, where you talk about kind of the overall objectives of your final project. Okay, but yeah, Friday will be dedicated exclusively to illustrating variance estimation in the software. Okay, I think we're all set for today then. So we will plan to see everybody in about an hour and 10 minutes at the lunch, those of you who are here in Ann Arbor. Everybody else, we will see you for the lab on Friday. Remember Friday, we're starting at 10 o'clock, not 9 o'clock for the lab sessions. Okay, all right, thanks everybody.
Can I ask? About my data that I sent you. And about your data, okay, and we did this. As of bootstrap and 200 and this give a scale. It's okay. I ended in the project.
Yep.
I put to use this scale when I declared the design.
So 1 second though. So when you created that as that SVR design, I saw you were deleting it. You were using RM immediately after you created it. I'm wondering why you're recreating a design object when you've already created it. So here, yeah, no, it's all right, it's all right. So here, you're taking the essential design information
Yeah.
and you're creating a design object,
Yeah.
right? You can just use that object in all your analysis.
No, but this is because I create in my company, this is backstage because I am in your project, I am using the website from my company, I am using the CSV data.
I see, okay.
And
So
I
you're
am
using the raw data.
Yeah,
Okay.
because the last time in DJ, we were working, I want that they work in the correct way. So I will declare that something, and the scale, okay, trap. But I saw that my data, my replication is not a weight thing, is not weighted, yes, the replication. It's like an index. I don't know if you normalize it. No.
You don't have to.
Okay.
But those look odd though. Why are they all 2, 1, and 0?
Yeah, I have, if in this function, I use this combined
I'm
with
guessing,
false.
I'm guessing the scale is adjusting each of those weights in some way based on the replication. Yeah, and then using false would help with that, but that's interesting that they're all that. So those are the replicate weights that came from as.sv rep design? Okay.
Came from.
Yeah, so the scale must be multiplying by them.
Yeah, and this combined weight to this there. But this is correct. I think our company is the even complicated thing. I think
Well, if you're gonna do this and provide those weights, just make sure that you also provide this code and say that, to analyze these data and use the replicate weights correctly, just make sure to use this particular R code so that data users can jump right to that. Yeah, that's the important thing in this case. Will just be making this clear in the documentation that this is what was done and this is the code that you have to follow to carry out the analysis. That's going to be the key.
I will say it to my boss.
Yeah. 100%. Yep.
Frequency and my design methods. Again, getting the two data missing in the image data set.
Well, hold on. So this is your PSU.
Yes, this is a PSU 269.
Is that how many PSUs do you have in total?
Yeah.
So there's 2,600 PSUs. Okay. That's a lot of PSUs.
Yes, a lot of PSUs. Basically, this was the provincial study. So and I have stratum like 80 stratum.
Okay.
But when I design it, so I guess I have 2 missing PSUs.
So let's just take a look. So set these. Go to survey set.
One is
go to survey set. Go to survey set, then set your PSU, then your weight, whatever that might be. Square brackets now.
So if you use that, you have already created
Okay. And then set your straight up.
You have not accounted for the design. That is
Okay, and then immediately after running this, say SVYDES.
You already accounted for the
So
like I am getting 78. So there are 2 stratum missing.
Okay.
So is there any there will be an impact on such kind of information on the final?
Well, so does it just mean that there's 2 codes there?
Yeah, two stratum information is missing, like one for like 54.
So 54 is
54. 53.
My question would be though, are there actual respondents in the data set coming from the stratum 54 and the stratum variable just has a missing value for those respondents?
Yeah, basically we get the information for each and every child from the household level.
Okay.
Yeah, so this is the weight has been set for the children 5% in each household.
Okay.
So from there we can have the information like for the PSUs. In every PSU we can see that how many children from 5 to 17 years.
Yeah.
I'm just saying. Are there, however many
there's about, say there's about 800 on average. Are there 800 cases in the data set that have a missing value code on Strava?
No, there is no mistake.
So they're just not there.
Yeah, but I was just amazed that there is no child for 5 to 7 in any specific study.
Yeah, it's possible. I mean, it's possible. But yeah, I would just use what you've been provided to do the actual variance estimation. It looks like you have plenty of clusters.
Yeah, exactly. So it's basically, we have 36 domains in our province, and each province is sample size has been determined.
Okay.
So here we are having, like, I'm going to use this final variance for my analysis.
Yep.
But I'm just for today's lecture, what I'm perceiving. So we need to define alternative methods as well.
Well, you don't have
If
to.
we
You already have the Strava cluster code, so you're fine. You can just use linearization.
Okay. So if we want to use these alternative methods, so we can use those.
Yeah, so what you would do, like, if you just tried doing a survey mean on some variable, right? Just pick one. Doesn't matter. Just try running that.
The Federal University of Brazil.
So like SPY colon mean, just some, doesn't matter. Just pick one. Okay, so that gives you your linearized variance. What you can do is say SVY comma, and then say VCE parentheses Jack. Now this is going to take a long time with your data set, right? Because you have so many clusters. Yeah. Without the H.
We need to
Take the H out.
in this.
You wrote KHN, just take the
Oh,
H
yeah.
out. There's two Ks.
And one more.
Say colon B. So this is gonna overwrite the default of linearization and do the standard jackknife without calibration adjustments. But it's gonna do it for all 2,692 clusters, so it's gonna take a while when you run this.
So if I run this with the
Just function. See, it's gonna look.
Oh, yeah.
It's gonna do that all the way up to 2,692. So this is the computational difference, right? And you're gonna see that the standard errors.
Oh, yeah. This is what we are.
But this is, again, this is just in working memory. So State is just doing this in working memory. You're not gonna get those replicate weights. It's just doing that for this particular analysis.
So we can have such variable jackknife weights in our data set. We can say-
Yeah, but the data producer would have to create it. State is not creating it for you here. It's just doing it temporarily to do the variance estimation. The data producer would actually have to form all 2,692 replicate weights to provide. But since you already have the Strava cluster code,
Yeah. So in some data sets, when we don't have like PSU codes and the strategy codes, so then there is a necessary thing, we need to go for this.
well, there's nothing you can do in that. As I said, you have to use the design effect adjustment of some kind, where you look at past surveys, multiply the variances by whatever the average design effects are. But if you're not given either replicate weights or the Strava cluster codes, there's really nothing else.
So how much time? normally?
Well, you can see. You can see.
Yeah.
That's what's unusual about your data set. Most data sets are gonna have like at most 100 clusters. So
it's
in
not
your data
going to
set,
2065.
yeah, in your data set, like if people here were working with this, we would combine so much just to form the larger sample area, because it doesn't really make a difference. So, but yeah, you'll just have to wait for the full 2692 to be.
Yes. So here on the slide, this is like, so when we started our lecture, set our desire, like we are going to alternative methods, like show the series and we have such alternative.
Yep.
And here we are saying that we don't have any PSU code and we don't have any stratum. But in the.
No. Here, the data producer does have that. They need that information to form these replicates.
Fine.
Yeah, they absolutely have to do
Fine. So when we are going for the JRR or ERR, so we do have any PSU codes and stratum code in our data set?
No, so the typical case, if you're just a secondary analyst, independent of the data producer, The typical case is that the data producer is gonna form the replicate weights for you and give them to you. And then you input them to the software. Okay, you're not responsible for that. You're responsible for analyzing the data. So you're responsible for seeing either are there stratum and cluster codes available or are there replicate weights available.
So
That's it.
being a data producer.
Being a
so
data producer,
if
you
we don't
to
have
decide.
PSU codes and strata codes, then we need to run this procedure.
Well, being a data producer, you do have these.
Yeah. we do
You're the
have
people who
this, yeah.
created the data.
Otherwise, we don't.
Otherwise, you can't do all
proceed.
this. You need that information to form these replicates. Yeah, as the data producer, you most definitely have those codes. You have to because you created the data. Yep.
Thank you so much.
Okay, thanks. Yeah, your thing should be done running.
Yeah, maybe.
Now you can compare the standard errors and see.
It's like.
Oh, it's still running. That's what I'm saying. Imagine, this is just a mean.
Yeah.
Imagine you gave somebody these replicate weights and they were fitting like a logistic regression model. They'd be sitting there for 10 hours. There's no point to it. Yes.
Yeah.
Can I have your
so-
signature in the?
Oh, jeez. No problem. Jeez, oh, Pete. Where would you like me to?
Anywhere,
Oh, okay.
where there's
Okay.
space.
That's me.
Okay.
that's where-
Jeez, you guys.
And date.
Oh, and date?
Yes.
Yeah, what is today's the 12th?
It's 6 to 8.
Cool, yeah.
Take the picture.
Cool.
Thank you.
Yeah, you're welcome.
Thank you.
Thank you. Here's your pen too.
I got the same,
Like,
same, thank you.
You're seeing the
Yeah.
point.
Same as standard.
So you waited 4 minutes for the same answer.
Yeah. Thank you.
so bro, this is the file that we will be using. I want to use, we wanted to use as a group on contraceptive.
Okay.
So, I have two questions. Like those ones, those files, so it's not this, can I remove those ones? Not as a variable, they are cases.
Okay, I don't know what those variables are. So.
Like this one is passes to the table for one family, an example, like this
Okay.
one. She passes to the table.
Yeah.
So the first person in the house only, the second person, those cases are more. You see, whether someone is twins or not. So yes, no, this is the case. So all of those from 1 to 20 were combined as one
Well,
file. Yes, no.
In the typical setup, right? This is telling me that there was some household that had 20 people.
Yes, and some, yeah, some was.
So you can combine them, yeah, but you just have to be
So
careful. about it.
the file has combined them.
Okay.
So can I remove those cases?
Sure.
Because
You don't need that. These are variables though, not cases.
Yeah, this is
You
the
can,
variable.
you can remove the variables, yes.
Yes. And on the other hand, I want to,
Yeah, you can just scroll.
yeah,
You gotta clean up this data set. This is-
no, they really provided the case I want here.
Sorry, I'm gonna turn this off real quick.